Okay, so let's look an example, a simple example based on chapter 7, sorry. So this is a simple flat plate. We have a simple flat plate which is at a temperature of 27 degrees Celsius, and there's a breeze blowing it over it at a speed of 10 meters per second, and the temperature, and it's pretty hot. The temperature of the air is 300 degrees Celsius. The length of this plate is 0.5 meters, and the plate is infinitely long, um, going into the page. And we have to find out what is the heat transfer per unit length, that is the heat transfer rate per width that is inside the page of the plate. So what your approach will be? Your approach will be that your the formula for your Q prime by Newton's law of cooling will be HA times delta T divided by the width. So this will be your H into L times T infinity minus Ts, and that's because T infinity is at a higher temperature. So you don't know what your H is, and you can calculate H using the relation between Nusselt number and H. So that relation is your Nusselt number, average Nusselt number with a subscript L, because we want it over the entire length, and because we want to calculate the heat transfer across the entire length of the plate, is average heat transfer coefficient multiplied by L divided by the thermal conductivity of the fluid, that's air. And we can write our H as Nusselt number times thermal conductivity of air divided by the length of the plate. Now we know that the general form of Nusselt number is it's C times Reynolds number to the power m times Prandtl number to the power n, and the values for C, m and n are different for different geometries, different types of flows and different materials. So our first step will be, so we will need to find out what our Reynolds number is, and for that we'll need different properties like our viscosity, our Prandtl number and thermal conductivity. So we will calculate our properties at an average temperature, which is also called as the film temperature. It's the average temperature between surface and air temperature, and we'll find our properties using table A.4. So the properties are usually given in table A.4, which is behind your text, which is at the end of your text in the in appendix A. So our first step here will be to identify the geometry. So we have a flat horizontal plate. Second step is to calculate the film temperature. So our film temperature approximately is 437 Kelvin. Comes out to be around 436.5, but I have just rounded it up. Our next step will be to calculate the properties that we require at this particular temperature. So our properties at uh, so our viscosity at film temperature will be 30.84 into 10 to the power minus 6 meters square per second. Thermal conductivity will be 36.4 into 10 to the power minus 3 watt per meter Kelvin, and the Prandtl number that's given is around 0.7. And according to the Prandtl number, let's say the value of n is 1 by 3. So in the next example video, I'll tell you how to read these values from the table given from table A.4. But for the purpose of this problem, let's say these are the values that I've calculated from the table. So moving forward, our next step will be to calculate the Reynolds number. So we know the velocity, we know the length of the plate, which will be our characteristic length, and we know the viscosity. So this will give us a Reynolds number of 1.62 into 10 to the power 5, which is less than our critical value. That means our flow is laminar. So now we need a correlation for the average Nusselt number. So based on the information that we have, that is a flat plate and a laminar flow, we can use equation 7.25 from the text, which is Nusselt number is equal to 0.664 times Reynolds number to the power half, Prandtl number to the power 1 by 3. And on substituting the values of Reynolds number and Prandtl number, we get a Nusselt number to be 237.4. So, yeah. Now we know that the relation of H and Nusselt number is this. Substituting value of Nusselt number in this relation, the value of thermal conductivity which we found from the table, and the length which is given, our overall heat transfer coefficient or average heat transfer coefficient comes out to be 17.3 watt per meter square Kelvin. So substituting that in the Newton's law of cooling, we get uh, heat transfer per unit length as 2359 watt per meter. So this is the H that we've calculated, L that is given, and the temperature difference in Kelvin that was also given in the problem. So uh, this gives us a heat rate per unit length at as 2359 watt per meter. So this is how you this is how you approach a simple problem where you have a flat plate. So make sure you understand the steps that we followed in this problem. These steps will be applicable for any problem that you solve in this chapter. So we basically identified the geometry, then calculated the film temperature, looked at the properties at the film temperature, found out the Reynolds number and what type of flow it was. Then we found out a proper correlation which we could use. Then using the correlation for Nusselt number, we calculated the Nusselt number, and based on our Nusselt number, we calculated our heat transfer coefficient and then our heat flux or heat per unit length in this equation, in this problem.